Hello and welcome back to the lecture on applied econometrics. So, we have been talking about probability distribution. In the previous lecture, we spoke about sampling. Now, in this lecture, we are going to talk about a very important natural law, which is going to, we will see that this law is going to be a foundation of many theorems that we are going to deal with. And this law is central limit theorem. This is essentially a natural law, and because it is a natural law, it has an all pervading application, be it in physics, be it in chemistry, mathematics, statistics, of course, economics. Everywhere we will see the application of this law. Now, what exactly is this law? So, I will just tell you few keywords which will help you to remember this law, and these keywords are: you can draw samples from any distribution in this world. You draw samples. If you draw the samples randomly, the first condition is you have to draw the samples randomly, and second, the sample size has to be large. So, from any distribution, whatever be the nature of the distribution, you draw samples, you draw them randomly, and you have sufficiently large sample size. If you do that and then you take sample means, what you will get is that the sample means you will see are normally distributed. Okay. So, I will write down the key points. So, first is that any distribution, let me use a different color, any distribution. So, irrespective of the distribution, any distribution, you can draw samples from any distributions, then you draw samples, you draw them randomly, you have to have a large sample size. If you do that, the sample means that you get in this exercise, you will see the sample means are normally distributed. Okay. The sample means are normally distributed. So, let me actually show you whatever just I have said, I will show you with some numbers. Okay. So, I actually have created a Excel sheet for you. Yeah. So, I used, if you remember in the previous lecture, we used some function called rand between. So, if you give this rand between command, so you can generate this random number. So, I have actually created this number somewhere else, and I copied it, pasted it here. So, I use the function paste special just to make sure that it does not change every time I click somewhere else. So, essentially I got all these random numbers. Yes, all these numbers you see here are random numbers generated using the rand between function. Now, once I have done that, I have taken 3. So, it is just randomly done, not arranged in ascending or descending order, just as it is. Then what I have done is I have taken a sample size of 3, like each 3 number I have taken 2 to 4 or 4 1 1, then 3 7 8, 1 3 9, 10 8 6, 10 6 2, 7 4 7, and so forth, and then I have taken their mean. Okay. So, that means 14 by 3, which is 4.66, then 4 2 6 by 3 is 2, then 3 7 10 18 by 3 is 6, then 3 plus 1 4, 13 by 3 is 4.33, 10 7 23 by 3 is 7.66, and so forth. Okay. So, all these means that we obtain, they are done using these 3 numbers. We got this means using these 3 numbers. Okay. So, we have got the sample mean. So, here the sample size is 3. You can actually increase the sample size to get a better result. Now, once I get the sample size, what I have done is I have used a separate sheet. I have sort of brought them together. So, here we have the mean values, the same value from the previous sheet. Now, once I get the mean values, now I have done some ascending or descending order, whichever order I wanted to organize the numbers, just because this will help me to sort of count the frequencies. Okay. Now, I have created several beans just because I need to count the frequencies. So, I have taken 2 or below, 3 or below. So, means 3 or 3 to 2 basically up to 2. 4 or below up to 3, 5 or below up to 4, 5 to 4, 6 or below basically 6 to 5, 7 or below 7 to 6, 8 or below 8 to 7 and 9 or below 9 to 8. Okay. So, this way we have counted the frequencies. So, let us see from this table how we can actually count the frequencies. So, 2 or below we have only one number 2, right. 3 or below we have only one number which is 3. 4 or below there is no number 4 or below. So, 4 and between 4 and 3 there is no number. Okay. Now, 5 or below we have this one, this one, this one, right, 3, we have 3 observations. 6 or below we have this one, this one, this one, this one and this one. So, when you are saying 6 or below we are counting 6 in. So, essentially that means we have 7 observations. Now, then we count 7 or below. So, we can take 7 or below. So, it is like 1, 2, 3, 4, 5. We have 5, 8 or below we have 7 and 7.66 which are 2 and then there is 8. Okay. So, these are the frequencies we have got. Now, with these frequencies if I now plot the, so these are basically the mean values that you obtain from the different samples, right, and their frequencies. Basically these are the mean values and these are their frequencies, all right. Now, if I plot these in a sort of just a bar chart, if you just plot simple bar chart and if I take this the data, if I change select data and I select data from here, and I OK it. So, then I will see something like this, some sort of this kind of curve. So, this essentially shows that it have that sort of a bell shaped curve nature. Okay. It has that bell shaped curve nature. You can actually increase the sample size and you can actually take larger number of observations and see this will actually gradually sort of come together and it will give you a beta sort of distribution. So, that we can actually do it, we can probably do in some assignment. So, this is essentially the essence of central limit theorem. So, irrespective of whatever distribution, so this is a random number. So, it is not from any distribution, it is a random number, this one random number, these numbers we got just a random number, but you can actually have a distribution, you can actually have a logarithmic or exponential or whichever distribution you think you want to take, you can take it and you take the numbers from there and you can actually do the experiment yourself. Okay. So, that is something that you should do. So, essentially the point is that we get this normal curve. Now, I will explain why do we get something like this, and this is this requires some bit of understanding, and whatever background, whatever knowledge we have gained so far in this course would be sufficient for us to explain why this this central limit theorem is actually observed in nature. Okay, and I will explain that, but before that I will share some stories with you. Okay, and how the central limit theorem is actually came into prominence. I think I told you about Francis Galton, and Francis Galton was a in his time he was a prodigy. So, his another claim of fame is that he is a cousin brother of Charles Darwin. As a matter of fact, Francis Galton had much more fame at his time than Charles Darwin. Charles Darwin at that time did not discover his master creations. So, Francis Galton, he was, so this is a story and he actually demonstrated central limit theorem in Royal Society. He was based in England. So, one evening, so he actually took something called Galton Board, okay, and the Galton Board is something like you probably have seen it. So, I will just show you. This is a Galton Board. So, let me actually, this I have taken it from internet. So, this is something like this. It's sort of a bean board, and you actually you can drop beans or some sort of metal balls inside it and see how the distribution looks like. So, what he did is he actually dropped this metal balls. You can see the metal balls on the top, and he actually dropped the metal balls inside the box, and what happened then is like this. Something like this. Now, essentially what you see is all the balls when falling from the top, they have a equal probability 0.5 of going towards left or right. Okay. Now, when the balls when they have a probability 0.5, it is actually very similar to the coin tossing experiment that we do when we actually explained the Bernoulli trial or binomial distribution or Bernoulli distribution. Okay. So, it is just like that, probability of success is 0.5, here also probability of success is 0.5. So, probability the ball goes left or right is 0.5. Now, so it can go either way. Now, why suddenly it has this kind of distribution? Why suddenly it is spiking up here, right? So, that is something we need to further see. And if you remember, when we did one example where we actually did the normal approximation to binomial distribution. So, when he gave the example of doctors in a hospital, if we have 5 doctors in a hospital and we wanted to see the probability of all the doctors getting infected when the probability of getting COVID is 0.2. Okay. And there we have actually showed that depending on your probability of success, you have a distribution that could be skewed or that could actually become a normal distribution. Okay. So, we have seen that even in binomial distribution, binomial distribution, we have seen that if P probability of success approximates to 0.5, the distribution also approximates to normal. Okay. Now, the point is that, so it is quite, it appears that it is quite natural. Everywhere we see that for an equal probability of things going left or right, we actually see something like a normal distribution. Okay. Why is that so? Okay. So, again, like before, I am trying to create some suspense. So, again I will show you another example. I am going to show you another example of like of something similar happening, and this is with an experiment of, let us say, sugar. Okay. So, I have a jar of sugar and I have a plate. Now, I want to see if what kind of distribution I will get if I was in the place of Galton. Okay. So, what I am going to do is I am going to actually pour some sugar on the plate, all right, and let us just do that. So, I am going to pour the sugar. So, it is a empty plate, no mystery magic here, it is just normal sugar, and it's let me just start pouring it. I will be careful. That is enough, I think. So, I hope you can see the hump like distribution, the bell shaped distribution, the normal curve type distribution here. It is exactly the same thing that Galton has seen, or it is exactly the same thing that you have seen when you are doing the normal approximation to binomial, when you are actually trying to see the infection rate of doctor and their probability of coming to office, right. So, essentially so all these examples or the same thing we have seen with our random number experiment. So, all the experiments we are doing is basically to show you the phenomena, what is happening here, that the normal curve is appearing from nowhere, right. Now, the point is why the normal curve is appearing, and that is what we will see now. Now, note something. So, one is that we have spoken, let us go back to the explanation of it. So, we have said that we need to draw the samples randomly. Okay. Draw the samples randomly. I will use a different color. Draw the samples randomly. Now, what happens if we draw samples randomly? So, when we draw samples randomly, we have previously explained that we have IID. We actually use IID random variable. When you are drawing samples randomly, we are getting IID random variable. Okay. And we will see why this criteria is so important here, this IID random variable when you explain the central limit theorem. Now, if we have IID random variable, we know that for IID random variable, let us say y is IID random variable and it follows some distribution, whatever distribution that is, it is a fixed mean. So, let us say mu and fixed standard deviation, let us say, or fixed variance sigma square. Okay. And this is going to be the mu and sigma square is going to be constant across the different random variables. Now, and it does not matter which distribution we are drawing it from. So, it does not have to be normal or anything, just for IID, these two are required to be constant across the different random variables, and one draw will not influence the other. So, they are basically independent. Okay. Now, when we are, let us say, when you are drawing samples randomly, let us say xi are all the different draws, and when we are drawing all the samples randomly, and what we are doing when we are actually doing the average thing, we are actually first before we get the means, we are actually summing them up, right. We first add them up, we are first adding these three numbers, we are getting the sum and then dividing it by 3. So, we have just done the whole exercise in one go, but we are actually summing them up. So, essentially first I am getting, let us say, a y which is sum total of xi. Okay. So, first I am summing them up. Now, xi are the random variables. So, basically I am adding the random variables. Now, when I add the random variables, what do you get? We have shown in our explanation from Bernoulli binomial, we have shown that when we add the random variables, let us say if my xi has a, let us say, Bernoulli distribution with mu and sigma square, then if I sum them up, so usually we write, okay, let me write mu sigma square, then my, for binomial distribution we will have n mu and n sigma square. Okay. Now, for sort of, to be very specific, the Bernoulli distribution mean is p, variance is p q, and then my y will follow a binomial distribution with n p comma n p q. All right. So, this is something we have seen. Now, in a similar fashion, when we have this in a similar fashion, so all we have done from Bernoulli to binomial, all we have done from Bernoulli to binomial, all we have done, we have basically added the random variables. So, here also what we are doing is we are actually adding the random variables. So, we have seen a binomial distribution could be derived from a Bernoulli distribution. All we have to do, repeated Bernoulli trial would, when you sum them up, we will get the Bernoulli binomial distribution. Now, in the same fashion, here what you are doing is when you are drawing these samples and we are getting the sample means. So, the first step of that is we are adding the samples, we are adding the random variables. Now, when you are adding the random variables, let us say all the xi's are representing the random variables, any distribution mu sigma square, and we are adding them up, we are getting y. Y is following, so let us say another distribution d1 and mu and sigma square. Okay. So, it is exactly the same thing as the previous one, where we had this one as Bernoulli and this is an binomial. Now, how come it is becoming a normal? Now, if you remember the binomial, any binomial distribution, we have shown it previously, could be approximated to normal when you have sort of large number of observations, right. When we have large number of observation, it actually becomes a normal distribution. Now, and the normality increases with larger n. Okay. Now, if I actually look at it, so it is basically the sum total of all the random variables, right. So, when you are doing a mean, we are actually dividing it by n, the total number of observations, right. We are getting a mean. Now, essentially the whole thing, when we, even before we actually take a mean, even if we just sum them up, that too will follow a normal distribution. So, that is something we have to remember about central limit theorem. It is sort of a rejoinder that when we add them up, when we add the numbers, when we add the random variables, that also will lead to normality. So, adding just adding the random variables would also lead to a normal distribution. So, you do not necessarily have to have the mean, like we claim the mean of the samples. We do not have to have the mean, but even if you have it, even if you like even if you do not have the mean, you can actually get a normal distribution, but if you have it, what you do essentially you divide it by n. So, basically you get x bar is let us say 1 by n summation x I, where summation y is equal to summation x I, right. And so, when you divide and y follows n mu comma n sigma square. So, when you divide that by n, you get x bar follows a normal distribution with mu sigma square. Okay. So, essentially what you have is that you prove that your claim about central limit theorem is correct. So, the mean of the randomly drawn sample would follow a normal distribution. Now, why we call large sample size? Another criteria was large sample size. We have to have a large sample size. Why do we claim large sample size? So, I will just you can intuitively understand that the large sample size part. So, let us say you are drawing sample size with sample size is equal to 1. In another case, you are drawing sample with sample size 5, let us say. Now, what will happen? Let us say if I draw with n is equal to 1. So, I will the mean of that value is going to be the value of the random variable itself, right. Whereas, if you get n equal to 5, you will get the mean as the mean of all those 5 random variables, right. Now, getting n equal to 1, what you will essentially will not be able to cancel out errors as compared to if you have n equal to 10 or 5 or 10 or 20 whatever. So, if you have larger n, what will happen the moment you take sample mean, in that sample mean all these observations they will cancel out their errors, right, and it will be more close to the population mean, right. So, as you increase the sample size and when you get the sample mean, you will get the number, you will get the value which is more close to the population mean. And that is the reason when you actually plot these two different distribution, you will see something like here. If you get something like this here, in this case you will see something more prominent normal curve more close to the population mean. So, that is the reason you prefer to have a larger sample size, because that will give you more sort of a better result. So, in our first example that we have given, we had sample size is equal to 3, but if we instead give a sample size of 10 or 15 or 20, we will see the result is actually improving. Okay. So, it will look more normal. So, that is basically the idea of central limit theorem. Now, I said that the central limit theorem we have to have the random variable has to be IID random variable, right, IID random variable. And why it has to be IID random variable? Because we have proved that if you do not have IID random variable, this Bernoulli to binomial conversion is not going to be happening, because that is the fundamental of this conversion, right. So, that is why it has to be IID random variable. The mu and sigma square has to be constant and they need to be independent. Now, what if a random variable is not IID? So, even then the central limit theorem can hold true. So, I will write for non-IID random variable, the central limit theorem can hold true under certain condition. Okay. There has to be some condition fulfilled. And what are the conditions? So, for IID random variable, so what is the difference between non-IID and IID random variable? So, since in IID random variable the mean and variance is constant, so we have equal weightage, whereas in non-IID random variable, since the mean and variance is not constant, so we have varied weightage, all right. So, we have varied weightage. So, instead, where for IID random variable we wrote y equal to summation of x I, here it will be y equal to summation of a I x I, where a I is the weight. So, this is for the IID random variable and this is for the non-IID random variable. Okay. Now, if we have a very large number of observation, it could be proved that this weight will not matter. So, essentially it will behave as if it is a IID random variable, and I am not going to prove that. So, it is something called Lyapunov CLT, central limit theorem. So, essentially you can also have the central limit theorem holding true for non-IID random variable if you have a very large number of observation or very large sample size. So, with this we sort of end the lecture on central limit theorem. In the next lecture we are going to actually talk about another natural law, which is law of large numbers. Thank you.